All right, boys. I have some updates to make. One thing is, I decided to go with PE fishing line, and the reason for that, instead of the nylon thread, which I was going to use for the robot's muscle tendons or muscles, however you want to say it, the reason I didn't go with nylon anymore is because it turns out if you want, like, let's say a 100-pound test of nylon, it'd be like 2 to 3 times the thickness of a 100-pound test of PE, which is polyethylene fishing line. So braided polyethylene fishing line is like 1/3 the size or one half the size for the same strength as nylon, and the nylon would be like upholstery thread. Um, so I still may use the nylon upholstery thread I was using for like facial expressions, like very um, not strength requiring at all. But for the fingers, I decided I did want something more beefy. I thought the nylon upholstery thread I was using was maybe 30 to 50 pound test, but that was just based on me like trying to pull it apart till it snapped, and I don't think that's the proper way to test it. That would give you a ballpark, but I think it was not accurate. And the real test of the string I had based on charts I looked at when I was researching was closer to 20-pound test, and that's really not so good for robot fingers. I feel like you would want probably a minimum of like 60-pound test, because like imagine if you're catching a football and the football's like hitting your fingers real hard, or if you're hanging like rock climbing and you're putting all your weight on the fingers. You want it to really be able to handle some serious weight. And plus, if you're getting something higher test, it's just going to be stronger in general, so it'll be less prone to snapping through, like fraying over time and eventually snapping. It, in other words, like just like with electronics, you want to design your electronics to be more than like double whatever. Like if you want 100 amps, you for like some motors, you want your electronics to be like 200 amp capable. So that you have um, capability to spare, like a buffer between what you're using as normal usage and total failure. That buffer should be pretty substantial, ideally. And by doing that, you become more rugged, more capable to handle extreme situations without things failing. So, what I went with, which is a significant step up from what I had, I was using 20-pound test, Clark's extra strong upholstery thread for the finger motors at first, for the winch system with the pulleys and everything for actuating the fingers of the robot. And now I'm using a 130-pound test PE fishing line. This is what the brand looks like. Dorcia Extreme Braid, 100 meters, 130-pound test. It's 0.63 millimeters in diameter. So you can see that's how it works. And to pair with this, I bought TPFE tubing, which is Teflon tubing that's hollow. It's got 1 millimeter ID and 2 millimeters OD. And I chose that because that's the closest we can get to for its ID to this thing's OD. So you want the string to not have much wiggle room in order to conserve on space and miniaturize the best we can. You want the ID of the tubing to be just bigger than the string's OD. That way it can fit in there easily, but doesn't have a lot of slop, which would just be wasted space. There'd be no benefit to it at all that I can think of. So the 1 millimeter ID, 2 millimeter OD, TPFE tubing, you can buy it on Amazon or eBay. I buy it both on eBay for cheaper, but you can buy it on Amazon um, for like 2 day shipping. But on eBay, you'll be ordering it from China, which will take like 3 weeks or something. So you can buy a little bit on Amazon, which will come right away while you wait for a larger amount to come on eBay. That's usually how I do it if I'm buying materials like this, just so I can use it right away. So let me show you guys how this looks in practice then on the robot. So there's your string, and there's the TPFE tubing going around a little pulley. And you can see how that's going to be. There it is. That's on the robot's arm. So that's one pulley of many. There's going to be multiple pulleys for the Archimedes pulley system I have planned. And so that's one big update. Basically, I was under the impression that nylon was the way to go because nylon's used in rock climbing. It's got some good stretch to it, and it just seemed like a very strong thing, and it's used for upholstery, so I figured that's a great thread to use. But nylon is used in fishing line as well, but only up to a point. Only up to like the first 10 to 15 pound test is nylon used, usually monofilament. But once you get past around 15-pound tests and you start getting into 50-pound tests, 100-pound tests, 200-pound tests, 300-pound tests, 500-pound tests, etc., nylon's off the table. You can't even buy nylon for that kind of test. Why? Because nylon would get way too thick at those higher test levels. Nylon just would get way too thick. And so for fishing line, they switched to polyethylene or PE fishing line once you cross that 15-pound barrier. And it makes sense because the nylon will get so thick it would not even be capable of like going onto a fishing reel. It would just be too thick. It'd be like a gigantic fishing reel because you'd be dealing with like fat rope instead of like skinny fishing line. And so that's why PE is used. Nylon just doesn't scale well. And that would be a game killer. That would be ruinous to my project because I do need something that stays relatively fine in diameter while being able to handle very high test. Because we're going to have the robot's big beefy motors that might, ultimately after down gearing be able to handle 500 or 1,000 pounds in theory. That would snap. That would snap most threads. So you want to have something that would be able to handle that. And I bought this 130-pound test one. I bought a 300-pound test one. And I bought a 500-pound test one. I think if I need to go above 500, I could probably just do two. I could just do like mix and match. Like I could use the 300-pound test one with the 130-pound test one, and then just like twist the pair of them in order to create 430-pound test. Or I could use two 500-pound test ones to create 1,000 pounds test and just twist together that pair. Or even just run them parallel rather than twisting them together. So there's different options there. I felt like 500 was a good stopping point. I think it might go up to 700 or 800-pound test. I don't think I saw anything bigger than that. But beyond that, I felt like maybe it'd get just too bulky even with the PE thread. So I might just run them like side by side to add up rather than twisting them. And then just run them through separate TPFE tubing if we get into those heavier numbers. But I have the luxury of not really, it doesn't seem like a very hard thing to pull off, like I said. Just two side by side should be fine in parallel tubes, and that should do it for 500 plus 500. That gives you a 1,000-pound test. And I don't think I need anything more than that. I don't think the motors I have are pulling that much, even with the down gearing. I don't think they're pulling a whole lot more than that. And what I did in my design process anyways is like, instead of having the quadricep have a single motor that just can lift the entire leg into a leg extension, like if you're at the gym, the leg extension uses your quads, rather than have a single motor with one string do that, I actually assigned 4 motors, one for each of the 4 quad means 4 quadriceps. So I assigned 4 motors to that, and each motor then would maybe only need to pull like 400 pounds for a total of 1,600 pounds of pull. And that would equate to a leg extension capability. If you were to sit on a machine with the robot, I think it'd be able to lift like 75 pounds or 80 pounds leg extensions. Why would it only lift 80 pounds when these motors are pulling 400 pounds? Why would it only lift 80 pounds when these motors are pulling 400 pounds? Why would it only lift 80 pounds when these motors are pulling 80 pounds when these motors are pulling 80 pounds? 1,600 pounds. Well, it has to do with like leverage because it's connecting to the shin bone. It's not connecting directly to those weights. And so to lift that shin bone, because the weights are out near the ankle, your your leverage where the muscle actually connects needs to lift significantly more weight because of location of the the location of the fulcrum, and then this is a lever. So like your motor might be only like a couple inches away from the fulcrum where the muscles tie in, the motor muscle, whatever you want to call it, the muscle ties in near that knee, and it's needing to lift with your ankle being like 2 feet away from the fulcrum. Um, the it's like, okay, if you put a five, if I okay, if I hold a broomstick, right? Let's just take this stick. If I use my right hand, if I put like a 5 pound weight on this end, if I use my right hand, I push up, I'm just lifting about 5 pounds. But if I put my hand over here and try to lift the 5 pound weight, like it'd actually be really hard. The further away it is from me, the more leverage this has against my right hand here. Um, so I'd be lifting like 20 or 30 times 5 pounds if I'm this close to this end of the stick. If I'm near the fulcrum, trying to lift that thing that which is way out there, and that's kind of the same type of mechanical disadvantage that the human body's muscles have to deal with and overcome, which is why you need like what seems like ridiculous forces to lift weights that are located near the extremities, like near the the hands or the feet. Um, like the muscles are generating way more force than you'd expect. And I have done some degree of calculating that stuff. I have some of that in my notes. I don't have it memorized. I've been accused, like on Reddit, that I haven't looked into that stuff, but that's not true. I have done calculations, um, but I don't have the luxury of just making a million calculations and then buying the perfect motor for that. Basically, like I wanted to stick to motors that are ubiquitous, which means like easily available and plentiful, that are accessible and benefit from the economies of scale. And so you're basically going to be limited to whatever motors are very popular for hobby markets like RC cars and RC planes and stuff, and then RC boats, and also for quadcopters. So those are pretty much the motors that you'll find on eBay. And I went through all the brushless DC motors I found on eBay and picked from that. Um, but we'll save more talk about some of the motor concerns for another video. This video's aim is to focus on the string update. So basically, nylon is out, and the downside to that is I'm losing some of that stretchiness, which I thought could be a good thing. The stretch can also be maybe a little bit of a bad thing because it could take away some accuracy, but um, I think accuracy is established ultimately by your potentiometers connected at the joints themselves, giving you feedback of the joint angles. Um, and so that's going to solve itself as far as being able to tweak the motors until the joint angles are right where they need to be. The advantage, though, of having your muscle tendons or whatever have some stretchiness to it would be like impact forces would be less hard on the muscles slash tendons if there's some stretch, because gives some give. If it's got no stretch capability, it might like permanently stretch it out and not be able to retract afterward, or it might just snap it in half in extreme cases, like if you threw the robot off a roof. It fell off a ladder or something and it landed. Maybe some of the muscle tendons could survive better if they had some stretch to it, but they just snap in half if there was no stretch. That type of thing. Um, they'd have less resiliency with no stretch in theory. Now, one thing that that'd be a potential downside to using polyethylene versus using nylon. But one potential upside to the polyethylene over nylon is polyethylene was said to be particularly supple, which means that it doesn't bark at you when you try to make tight bends with it. And so that could be a very good thing in order to give it longevity when it's wrapping around my pulley systems. If it's more supple, it can handle taking those tight turns around these pulleys without, um, I guess, fatiguing the string. There's something to do. They said like there's a minimum diameter you want on pulleys for different types of materials, because if you make too tight of turns, it like stresses out and causes premature failure of the string you're trying to pull around a pulley or the rope or what have you. This is particularly prevalent, I believe, in like steel braided rope. I'm not sure how much that factors into these synthetic ropes like nylon and polyethylene. I'm not sure if that's as big as a factor. I think these are more supple than steel, so they can make the tight turns without damage as quickly, but it still has to be taken in as a factor. And as I showed you guys the pulley earlier, I gave it a kind of conservative bend. I didn't make a real tight bend, even though that would save on space taken by the pulley systems. It um, would potentially be overly hard on the string going through that pulley through time by creating like a fatigue point since it's trying to turn too tight of a turn. So that's something I discovered that I never thought of before. Like some of my earliest pulley ideas and designs involved the pulley just going around like a really tight little stirrup. But my concern was that once I found out that taking too tight of a turn is very hard on the rope and it can cause it to snap over time, then I got rid of that idea and I just took a more conservative, like arching turn instead of like a very tight one. I just went more of like a hoop, and that will be uh, helping it in long run. And also, it might even help reduce friction, even though there's more contact area. Um, the more gentle sloping directional change could help reduce friction somehow in some way, I think, but that's theoretical. I'd have to test that, but I think it would. And we're going to talk more about friction in a upcoming video because there's been a lot of people mentioning concerns about friction in my Archimedes compact pulley design, and I think there could be some upsides to frictions I want to talk about later. All right, so that's it for this video.